We are going to use partial fraction decomposition to solve the first integral. Let's take the function which is integrated and decompose it into partial fractions. Here, this can be written in this way. We extract x, we extract 2, and we obtain 1 over x plus 2 times x plus 1. So we will decompose it into partial fractions. A over x plus 2 plus b over x plus 1. Now let's put it back under the common denominator. We have a times x plus a times 1 plus b times x plus b times 2, and I write it down as a plus b times x plus a plus 2b. So this is the coefficient which multiplies x, and this is the coefficient which multiplies 1. Since here on the left hand side we have only 1 and the coefficient next to x is equal to 0, it follows that a plus b must be equal to 0. Also, since the coefficient next to 1 is equal to 1, it follows that a plus 2b is equal to 1. We can easily solve this by subtracting the first equation from the second equation, and we can obtain that b is equal to 1, and therefore a must be equal to minus 1. Now that we know a and b, we can use this partial fraction decomposition to solve the integral. So we can write down this integral as a sum of two integrals, where the first integral is minus 1 of x plus 2 dx, and the second integral is the integral of 1 of x plus 1 dx. Both are definite integrals. Both can easily be solved, so we obtain minus ln of x plus 2 absolute value, and in limits between 0 and 1 plus ln of absolute value of x plus 1. Once again, limits from 0 to 1. We plug in the limits. We obtain minus ln of 3 plus ln of 2 plus ln of 2 minus ln of 1, and this is equal to 2 times ln of 2 minus ln of 3, because ln of 1 is equal to 1, which is equal to ln of 4 minus ln of 3, which is equal to ln of 4 over 3. Now let's go for the part B. In the part B, we'll use integration by parts. I write it down so that I write down ln of x first, just to show that for the integration by parts, for which the general formula looks like this, we have a function u of x and we have dv of x. And when we try to solve this integral, we are stuck because it's difficult to solve, but we can write down this integral in terms of a simpler integral. We have u of x times v of x minus this integral, which should be simpler to solve, v of x times du of x. So in our case, ln of x represents u of x, and this, what remains, is dv of x. As a rule, functions like ln of x, which are difficult to integrate, necessarily have to be u of x, because it's easy to differentiate them, but it's difficult to integrate them. U of x is the function which will be differentiated in this case. So ln of x is u of x. Everything that remains is dv of x. But of course, dv of x should be easy to integrate. And ideally, we should get a simpler expression here in this integral v of x du of x than the expression that we started with, integral of u of x dv of x. So let's write this down. U is equal to ln of x. We differentiate this and obtain du is 1 over x dx, and dv is equal to x squared dx. We integrate this and obtain that v is equal to x to the power of 3 over 3. So we multiply u times v, and we get x to the power of 3 over 3 times ln of x, and now we have minus the integral of v times du. This 1 over 3 can be extracted, and we have the integral of x to the power of 3 over x, which is x to the power of 2 dx. We can easily solve this. X to the power of 3 over 3 times ln of x minus x to the power of 3 over 9 plus a constant c, since we're dealing with an indefinite integral.